We have already studied the first type of DC to DC converter. It was a buck converter, that is a step down chopper. Now let us study the boost converter. So whenever we want to increase the output voltage higher than the input voltage, we generally use boost converter, DC to DC boost converter. So this is a circuit. Kindly observe here in the diagram. On the left hand side, this is the step up chopper or a boost converter circuit, and on the right hand side, these are the voltage and current waveforms for the various ports in the circuit. So we will first understand the circuit operation. First of all, we should note that boost converter is capable of producing output voltage higher than the input voltage. So this E0 will be higher than EDC. EDC is the input voltage and this E0 is the output voltage. So let us go through the circuit operation and understand how this circuit works, how is it possible to get higher output voltage. So we will go through the circuit diagram and understand the operation. Assume that initially the supply is connected and the transistor switch or the chopper is indicated here. Switch is indicated as a chopper. This is alternate way of writing the main transistor switch as a chopper. So when this switch is on, so what will happen is that when the switch is on, so this point will be connected to this point, isn't it? So when the switch is on, at that time the current will start flowing from the supply like this. It will come through the inductor L, and through the switch the circuit is getting completed, and from here it will travel back all the way to the supply. So current will be flowing from EDC plus L, then this chopper, and back to EDC minus. So this is how this circuit is getting completed. When the current flows through the inductor being an energy storing element, it will store the energy across it. Please note, at this point of time, since this circuit is closed, so it's a sort of a short circuit across the output. So in this case the diode will not conduct, and similarly there is no current flowing through the load. At this point of time there is no current flowing through the diode, neither flowing through the load, because whatever current flows, because this circuit is closed here, so current will not be proceeding ahead like this, rather it will flow here in a closed path with source, inductor and a chopper. So this is the first stage, and during this process the energy will be stored in the inductor. Now in the second stage we will see, okay, at the same time let us observe here what is happening in the waveform. Please see the output voltage here, V0. When the switch is on in the initial stage, you see that the output voltage here is 0, as I told you. No current will flow on the right hand side of the switch because the switch is closed, so output voltage is 0, right? And at the same time the current that was flowing, here it is indicated, the current will be increasing gradually because of the inductor. Inductor does not allow the current to suddenly rise, so current rises lightly. So this IL represents the inductor current, and similarly the current flowing through the diode ID is indicated here. So in this particular range, when the switch is on, so diode current is also 0. Let us now move ahead and understand the operation for when the switch is turned off. Okay, so when the switch is turned off, let us now again draw the current path. So when the switch is turned off, so this will be off, right? So it will be open circuit. At this point of time, the energy stored in the inductor, which was carrying current like this earlier, okay, see, when we turn off, the current flowing through this particular branch, it will tend to stop, it will stop, but energy stored in the inductor will induce a reverse voltage across it. it tries to maintain the current flow in the same direction, although through a different path. So what is that path? So that path is indicated here. It will be starting from plus terminal, the ADC positive, okay, then inductor, right, and then it now switch is closed, so current will be flowing through the diode, through the load, right, and back to ADC minus. So this is the direction of current flow when the switch is off. So this is off, inductor energy will be released and diode will conduct and voltage will be appearing across the output. So observe on the waveform here. On waveform we can see as the energy stored in the inductor gets released, the current tends to decrease gradually, and at the same time this is the output voltage. Since diode conducts because of the forward bias applied by the source, the diode will conduct. Energy in the inductor along with the source put together, they will forward bias this diode, so diode will conduct. That's why we can see that there is a rise in current across the diode, and as inductor energy gets exhausted, the current will flow through the load, right, and we'll get the output. So during the turn on time, the output is 0. During the turn off time, the output is equal to the input voltage. And plus, apart from the input voltage, so there is addition of two voltages here, right. The output voltage is sum of actually two voltages, that is supply voltage here plus minus, okay. So output voltage will be equal to EDC plus EL, voltage across inductor, isn't it? So net output voltage that will be available across the load or the motor connected at the output of boost converter will be sum of EDC and EL. The energy stored in the inductor is added to the energy coming from the battery or the source. So the net voltage available across the output will be higher than the input voltage because of the energy released by the inductor. So this we can understand. So difference in this waveform compared to the earlier waveform for the buck converter. In case of buck converter, when the switches were on, the output was available. When the switches were off, output was not available. But for the boost converter, here you can see it is the reverse way, and so also the output voltage is higher than the input voltage. Let us now proceed ahead and understand the characteristic equation. So please observe here, this is the characteristic equation for the boost converter. The relationship between output voltage and input voltage is expressed as output voltage upon input voltage is equal to 1 upon 1 minus duty ratio or the duty cycle. Again, the definition for the duty cycle remains very much the same as in case of buck converter. Okay, so duty ratio D is equal to turn on time upon turn on time plus turn off time. So T on is the on time for the switch and T off is the off time for the switch. So we get output voltage is equal to 1 upon 1 minus D times of input voltage. Let us consider one example. Consider that the duty ratio D for the boost converter in this case is set to 0.75, or we can say 75%. So we would like to calculate what will be the output voltage if the input voltage is 48 volts. So in this case, we just have to substitute 0.75 here as a value of D, and value of input voltage is 48 volts. So if you try to solve this equation, this will be 1 upon 1 minus 0.75. So that is 1 upon 0.25. So 1 upon 0.25 is like 4. So if the input voltage is 48 volts, the output voltage will be 4 times the input voltage, that is a 48 volts. Okay. So 4 times of 48 volts will be equal to, this will be like 192 volts. Now let us move ahead and understand the operation. Let us now understand the operation of third type of DC to DC converter. It is the buck boost converter, right? So It is a combination of buck converter as well as boost converter. A single circuit is able to perform both the tasks, that is stepping up the voltage and also stepping down as per the requirement. So the average output voltage can be regulated as per the need. Please observe on the left hand side, this is the circuit diagram, and on the right hand side there are waveforms. So within circuit diagram, the main elements indicated here are this is a transistor switch, and then we have a freewheeling diode, and then the energy storing element inductor, and the load means a motor. Okay. In the waveform also we are indicating several different parameters. The very first waveform here, it shows the on off status of the transistor switch. So it shows the duration with respect to time, for how much time the switch is on and for how much duration switch is off. Okay. Then the second waveform is the load current IL, having certain minimum and maximum values, IL minimum, IL max, and this again with respect to time. Then the voltage across the inductance VL. Okay, again it is having positive as well as negative polarity, as per we'll see how the operation takes place. And lastly ID. So this ID is the diode current. Okay, so let us understand the operation of the chopper. So while we study the operation, we'll go step by step through the waveform. Initially we can see that the switch is on. So we'll indicate the status of the switch here on the diagram. Kindly observe the diagram. I'll close this. So when the switch is on, so that is indicated here also as a T on. During this time, what will happen? How will the current flow? So when the switch is on, we see that the supply voltage, that is input voltage EDC, it will apply a forward bias to the it will apply a voltage which will reverse bias the diode. Okay, so diode will be reverse biased. Okay, and the current, since this is the reverse bias, so no current will be flowing through the diode, and hence no current will be coming across, no voltage will be appearing across the output. In such a case, the current that will flow when the switch is on will follow this particular path. So we observe here that the current will be flowing like this clockwise. It will start from plus EDC, it will go through the switch, then inductor L, and then back to the source. So as the current flows, the current flowing through the inductor, you can observe on the diagram, the inductor current rises gradually like this. Inductor current rises gradually, and so also the voltage will be appearing across the inductor like this. So this is the voltage on the waveform. So the polarity of this voltage will be like this, plus minus. Okay, so voltage polarity will be like this. Now after certain time duration T on, the switch will be turned off. So when the switch is turned off, we know that since current is flowing through the inductor, so inductor will store some energy. Please observe the polarity of voltage across inductor. It is positive. Positive means the upper terminal is positive, lower is negative. Here the diagram that is indicated, it shows the direction of current flow, and so also the polarity of voltage across inductor as a reverse. So this polarity will occur when current flows like this. Okay, during the other half cycle of the duty ratio. Let us now understand the further operation. Okay, now let us consider that we are now moving towards the second part, that is when the switch is turned off. So kindly observe on the waveform, the switch is turned off. So what will happen when switch is turned off? So this will not conduct, this will not be conducting, right? And the voltage across inductor, which was earlier having polarity like this, right? This was the original polarity, red color. It will undergo the change in polarity because the supply is now disconnected because the switch is open. So whatever energy is stored inside the inductor, this will try to maintain the current in the same direction. Although no current is being supplied, but energy is stored in it. So for supplying the current in the same direction, the voltage induced across inductor will reverse its polarity. So the new polarity across the inductor when it is supplying current when the switch is off will be like this. Okay. So what is the direction of current? The direction of current that will flow will be through inductor, through the load, okay, and then through the diode like this. So current will flow in an anti-clockwise manner, and again it will come back to the inductor. So that is why we see from the waveform that as the power source is not connected, whatever energy is stored on the inductor, that itself, that's a limited energy. It is not a source. It stores a limited amount of energy. So that is why as it supplies the energy, the inductor current will tend to fall. The inductor current gradually decreases. The energy is getting consumed. And while this is happening, the polarity of voltage across inductor is also reversed, because it tries to maintain the current in the same direction, although it is not connected to the source. So this release of energy, it provides current through the load, and it will enable this diode to also conduct. So diode will conduct, okay, because the diode will be forward bias because of this voltage appearing across the inductor. So when the diode is forward bias, the current will flow like this in this particular fashion, and that's why we see that even diode current has the same nature as that of an inductor current. As inductor current decreases, same current is flowing through the diode, that will also decrease. And once the energy stored in the inductor is exhausted, in the next cycle again we turn on the switch. And the similar processes will follow as this conduction continues. So the switch remains on for some certain turn on time, and then switch remains off, and then this cycle is repeated, right? So this is how the buck boost converter will operate. Now one thing we have to note here is that this converter is capable of producing voltages which are either higher than the input voltage, or the voltages which are lower than the input voltage. Okay, so how that is possible? That is possible by proper selection of this particular element, that is a duty ratio. So that we are going to check in the form of a characteristic equation. So the characteristic equation for buck boost converter is the output voltage upon input voltage. In this case will be d upon 1 minus t, where d represents T on upon T on plus T off. T on is the on time of the switch, and T off is the off time. If we observe this equation carefully, right, for values of d lying in the range of 0 to 0.5, okay, the circuit will act as a step down chopper, or it will work as a buck converter. And if we substitute the value of d lying in the range of 0.5 to 1, right, this circuit will work as a step up chopper. So we note here that both the operations are possible, step down and step up. Same circuit, same 3 element, but with the proper connection we are able to get both types of output from the same circuit. Okay, so it is quite versatile and will be useful in applications where we need to adjust voltage in either direction, higher than input voltage or lower than input voltage. So you can try out this problem. Again, consider the value of duty ratio to be equal to 0.25 and calculate the output voltage if the input voltage is 48. And after that, try to adjust the value of duty cycle above 0.5, let us say 0.5, and again calculate the output voltage, just as a matter of understanding the concept of buck boost converter.